We arrive to our last topic in AP Physics 1, where we look at a different type of circuit from a series circuit known as a parallel circuit. So we'll specifically look at what is a parallel circuit, what advantages does a parallel circuit have over a series circuit, how are they different, and how do we analyze a parallel circuit. So we looked at, in 9.2, we looked at a series circuit such as this, where we have light bulbs or resistors are arranged one right after the other, what we called in series. So let's suppose we have this middle light bulb burn out right here, okay? Or we have this last light bulb burn out right here. How are any of our electrons going to get from one battery, say the negative terminal, to the positive terminal, okay? There's no current that's able to flow. This is kind of like placing a dam in a river. The dam in the river is going to block everything. It breaks off of the flow. It breaks off the river, so nothing can flow. So if a light bulb burns out in a series circuit, we can't have any current flowing throughout. So how do we circumvent this problem right here, okay? So in everyday life, if we wanted to get rid of if we had a dam or we had a roadblock or anything like that blocking our path, what we could do is take an alternative path around in order to reach our destination. So in a similar way, we can do that same thing with what's known as a parallel circuit. So in this case right here, instead of arranging our light bulbs in series, we arrange our light bulbs at the same spot in the circuit right next to each other, what we call in parallel branches. So the resistors in this case are added in branches, what we say in parallel, because it looks like they're added in parallel lines. Okay? So in this case right here, what's going to happen is if this light bulb burns out right here, the current that's going through this light bulb won't be able to flow through this light bulb anymore, but it'll still have two other pathways through which it can flow. Just the same way that if there is a roadblock on a road, we can take a detour to get around that roadblock. All right, so one interesting thing about parallel circuits here is that in contrast to series circuits, in parallel circuits, if you add more resistors in parallel, the overall resistance of the branches and the overall resistance of the circuit will actually decrease. So how does this make any sense? Why would adding more resistors in parallel decrease the overall resistance of the circuit? So to think about this, we need to think about it from the perspective of, again, kind of like a roadway like we talked about, okay? So let's say we have a single resistor, all right? Our flow in this case, our currents of electrons are going to be cars. So we have a single resistor in this case. A resistor we can think of as a toll booth, okay? So if we place three resistors in series like this, that's going to be three toll booths in a row that cars have to pass through, which is going to constrict and slow down traffic, aka it's going to lower the current on our roadway here, or the current in our circuit, just like we talked about with the series circuit, okay? But with a parallel circuit, if we place all our toll booths in parallel, that means there's going to be more options for our cars to choose from, and thus traffic is going to be able to flow easier. The more toll booths we add, the more cars we can fit in and pass through per second. So as a result, the current will increase as the current of traffic will increase as we add more resistors in parallel. Likewise, the same thing's happening inside of a circuit. If we add more resistors in parallel, there's more paths for electrons to choose from, and thus more electrons are able to flow per second, causing an increase in current in a parallel circuit. Another interesting thing to note is that with a parallel circuit, regardless of the resistance in each individual branch, the voltage drop across each branch will be the same. So if each of these light bulbs have vastly different resistances, the voltage drop across each branch will still be the same. So if this has a resistance of R1, this has R2, and this has R3, then V1 will equal V2 will equal V3. Why does that happen though? That's so weird to think about. So we now might move back to the river analogy, okay? If we think about the resistance as how wide our circuit is, or excuse me, how wide our wire is, or how wide our river is, better said, we can see that the resistance will affect the current flowing through each branch of our parallel circuit. All right, branches that are wider, aka have less resistance, can have more current flowing through them, whereas branches that are narrower will have less current flowing through them. However, recall that we talked about how the voltage drop is like the drop across a waterfall. So each of these branches right here are going to be dropping the same amount of height from right here where the branches start to where they end at the base of the mountain. So as a result, the voltage drop across each resistor is going to be the same because the height drop for each river is the same. So that's the way that we can think about it, is that there's a lot of analogies between gravitational theory, aka the drop in potential energy, and resistors and circuits, aka the voltage drop in a parallel circuit. So the two big things to come away from this slide right here is that resistors added in parallel will actually increase the current and decrease the overall resistance, and that the voltage drop across each branch of a parallel circuit is the same. Okay? Next, we arrive to Kirchhoff's junction rule, which is another useful rule that we can use for circuit analysis. So Kirchhoff's junction rule states that the current entering any junction must be equal to the current leaving this junction. This rule is an extension of charge conservation. Because we can't have charge destroyed or charge leaving our circuits, that means the amount of charge flowing into a certain node or any junction, like let's say junction A right here, must be equal to the current coming out. All right, so that's like water flowing into different branches. The water flowing into different branches must be the same as the water coming out of those branches, okay? So if we have a current of 11 amperes that gets broken up into two different branches, the sum of the currents in those two branches must be equal to 11 amperes. So 4 plus 7 must give you 11, okay? Nice little rhyme there. However, this does not mean that the current in each parallel branch is equal, okay? So the current in this branch does not have to be equal to the current in this branch. Like the streams above, like the streams we talked about last slide, the amount of current entering a parallel branch depends on the resistance of each branch. Okay? So a branch with less resistance will have more current than a branch with more resistance. Okay? And current is going to prefer the path of least resistance, like we've talked about with our water analogies and river analogies. So what we can see right here is that I3 is going to have the pathway with I3 is going to have a higher resistance than the pathway of I2. Because I3 has less current flowing into it than I2, which means that there must be a higher resistance in I3 than in the pathway containing I2. Current will always prefer the path of least resistance. Okay? So as a result, whenever we have a junction, the current going into that junction is going to equal to the sum of all the currents coming out of that junction. I1 plus I2 plus blah, 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 blah. Okay? So next we come up to equivalent and total resistance in parallel circuit, okay? So in order to derive the equation for the equivalent / total resistance in parallel circuit, what we take note of is with Kirchhoff's loop rule, we're going to have the total current in the circuit is going to equal the current through each of the branches added together. So if this is our total current, then it's going to equal to the current in branch 1 plus the current in branch 2 plus so on and so forth. So what we can do is replace this with Ohm's law, where we have the overall current is equal to the overall voltage divided by the equivalent resistance. And then we have the voltage in R1 divided by R1, and then the voltage in R2 divided by R2, so on and so forth. But because our voltage drops across each branch are the same, that means the voltage drop for each branch is going to be equal to the voltage drop for each battery. So as a result, we can divide both sides by V, and that gives us the resistance for a parallel circuit. 1 over R equivalent equals 1 over R1 plus 1 over R2 plus blah, 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 1 over Rn, okay? So you're going to have to add fractions together and then take a reciprocal of that fraction at the end to get your equivalent resistance for a parallel circuit, okay? Which again, can be a little bit tricky here, so we'll see how to do it with a problem here in a second. So let's take a look at an analysis of a parallel circuit, okay? Again, we have these three rules that we now have, okay? We have that the voltage across all parallel branches are the same, and that we have the sum of currents in all branches is going to be equal to the total current going into those branches or coming out of those branches, okay? And then lastly, we have the equivalent resistance equation. The equivalent resistance equation is on your equation sheet, so you do not need to memorize it, okay? So we start out the same as usual, okay? Let's say we have a circuit that has a total current of 5 amperes, and it has 3 resistors arranged in parallel. Resistor R1 with resistance of 5 ohms, resistor R2 with a resistor of 6 ohms, and resistor R3 with a resistor of 10 ohms, okay? And let's say right here we have a negative terminal, and then we have a positive terminal, okay? I actually don't know why I say that. That's not really too useful for us, okay? So we can start by doing is filling out the resistance part. So we have R1 is 5 ohms, R2 is 6 ohms, R3 is 10 ohms, and then we can fill out the equivalent current, the total current in the circuit, which is 5 ohms, okay? So moving on, let's do a little bit of analysis here. So please note, with a parallel circuit, we cannot just add 5, 6, and 10 together to get our equivalent resistance. We now have to use the equation for equivalent resistance for parallel circuits. So we're going to have 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3, which gives us 1/5 plus 1/6 plus 1/10. And if we combine those together using a calculator, we're going to get 1 over R equivalent equals 0.46. However, this does not mean our equivalent resistance is equal to 0.46. What it actually tells us is that our reciprocal of the equivalent resistance is 0.46. So we have to take the reciprocal of 0.46 to find our equivalent resistance, which is 2.14 ohms. Okay? So as a result, we can see that our overall resistance is actually lower than any individual resistor making up our branches, confirming what we were talking about before, that adding more resistors in a parallel circuit decreases the overall resistance. Quite interesting. So now what we're going to do here, all right, is we have two pieces of information available to us in our equivalent row. So now we're going to determine the voltage and the power in our equivalent row here. Okay? So the voltage we can determine using Ohm's law. So we use total voltage equals total current times our equivalent resistance. So voltage is going to be 5 amperes times 2.14 ohms, which gives us 10.71 volts. Okay? And then our power we get by taking our current squared times our equivalent resistance, which gives us 5 squared times 2.14, or 53.6 watts. Okay? Now right here you may have noticed I have filled out this whole entire column of voltage with 10.71 volts. How did I do that if I didn't know anything else going on in these R1, R2, and R3 rows besides the resistance? Well, again, that's where we make use of the fact, again, that the voltage drop across each branch is going to be the same and thus equal to the voltage of the battery. So the voltage drop across each branch is going to be 10.71 volts. So now we have enough information in each of our rows here for each of our resistors to determine the current through each resistor and the power through each resistor, power being dissipated through each resistor. Okay? So we carry out a whole bunch of calculations here, and as a result of applying Ohm's law to R1, we get 2.14 amperes. As a result of applying Ohm's law to R2, we get 1.79 amperes passes through R2, and then through R3 we get 1.07 amperes through I3. And then applying an equation to determine the power through each resistor, we get that the power is 22.9 watts through resistor 1. The power dissipated through resistor 2 is 19.1 watts. And then the power dissipated through resistor 3 is going to be 11.6 watts. Okay? So this is what our table looks like right here. Here's our currents that we calculated, and here's our powers that we calculated in the last slide. Okay? So let's make sure this makes sense right here, okay? So notice that the branches with higher resistance have lower current and thus lesser power dissipated. Again, current prefers the path of least resistance, okay? So if we look right here, the 5 ohm path has the most amount of current passing through it, whereas the 10 ohm path has the least amount of current passing through it, confirming what we'd expect to happen. And then likewise, the 5 ohm resistor has the most amount of power dissipated through it because it has the highest amount of current passing through it. And then the 10 ohm resistor has the least amount of power dissipated because it has the least amount of current flowing through it. Again, current is the primary judge that determines how much power is dissipated in a component. It's not the only judge as we've seen, but it's the primary factor that we've seen, okay? In the current column, Kirchhoff's junction rule is met, so our overall sum of currents is met. 2.14 plus 1.79 plus 1.07 will give you something painstakingly close to 5 amperes. It's just not all the way there yet. Actually, it is all the way there yet. Yes, it is. So I have all my numbers rounded up nice and accurately. Okay? And then lastly, we can check conservation of energy. The sum of power dissipated across all branches is 53.6 watts. So if we add 22.9 and 19.1, 11.6, we're going to get that the power dissipated is 53.6 watts. And thus, again, this is how we can apply a verb chart for parallel circuit. We combine the features of what we know about parallel circuits with Ohm's law and the power dissipated, and then we can use that with the fact that if we know any two pieces of information in a row, we can figure out the rest of information in that row. And thus is how we analyze a parallel circuit.